Okay, now for question 7, and question 7 is the electric field question. And so what we have is that a -3 nanocoulomb charge Q1 is placed 10 centimeters away from a +3 nanocoulomb coulomb charge Q2, as shown in the diagram. Okay, so there you can see it clearly. The first question, draw the electric field pattern formed between them. Okay, so charges flow from positive to negative. So you see from positive to negative, this was perfectly drawn, well done. And then they form this as if they're being pulled towards one another, the ones that are not directly opposite each other. The lines directly opposite each other, they go, they're straight lines. The next question, a -2 nanocoulomb charge Q3 is placed 5 centimeters away from Q2 as indicated in the diagram below. So notice how it's placed directly at a 90-degree angle from Q2. Draw a force diagram showing the electrostatic forces exerted by Q1 and Q3, sorry. And so this is perfect. This is the force, and so what is happening? So forces again go from positive to negative. So our force is from this direction in that direction. So what will happen to a positive charge? It will be pulled in the direction of the negative. That's how we will look at the direction of the force. So here again, if a positive charge is there, then what is the -2 doing? It is pulling him in this direction. So once again, there's a pulling in this direction. If this was the same sign, so if this was also positive, it would have been pushing it in an upward direction. So this is a beautiful sketch. The next one is calculate the net force exerted by Q2 on Q2 by Q1 and Q3 respectively. Now, I think the way that this was answered or stated is confusing, because when you say respectively, you mean what is the net force exerted by Q1 and what is the net force exerted by Q3? Well, I don't think that is the question. I think we have to work out what is the force exerted by Q1, what is the force exerted by Q2, and considering these two forces, what would be the net force if we put them head to tail? And that would have created a 90-degree triangle. So let's answer that question on what would be the net force. And this unfortunately is not correct. If we look at our formulas, how do we calculate force? Okay, where are those formulas? Here we go. Okay. So the force exerted is equal, so here you can see here's the force is equal to the electric field times, here we go. The force exerted is equal to K times the charges between the two times R squared. So here the student, I'm not exactly sure, 2.16, it's maybe what he did there, not exactly sure, but that is going to be our calculation. So here, I just go back there, open up my drawing. Okay, let's see if we can do it this way. Okay, so here we have our formula is that the force is equal to K times Q1 Q2 over R squared. So if we just did it respectively, and so the way I would have answered this question is to first do it respectively and then find the net force. So here K is the 9 times 9 to the power of 9 times 10 to the power of 9. So K is 9 times 10 to the power of 9, and then Q1 is now the charge on, I'm going too far, so we're doing this one, so Q1 and Q3, so the one is -3 times 10, because it's nanocoulomb, nano is to the power of 9, not 19, times 10 to the power of -9, and then +3 times 10 to the power of -9 divided by, and then my radius between the two is 10 centimeters. 10 centimeters is 0,1 meters. That's important. Should change it to meters, and that should be squared. Okay, and so 100 centimeters is 1 meter. So 10 centimeters is 100 millimeters, and 100 millimeters is 0.1 meters. So let's just do this. This is 9 times 3 times 3, that's 81. So 81 divided by 0.0, or just 0.1 squared, okay, and it's negative 81, and then so that is 8,1 times 10 to the power of 1, 2, 3. So times 10 to the power of 3, this must be a 3, plus 9, because I haven't done the 10s. So 3 plus 9 is 12. 12 minus 18 is negative 6. Okay, so that, just once again, to check that, that's 9 times 3 times 3 is equal to 81 divided by 0.1 squared is 88,1 to the power of 1, 2, 3 to the power of 3 plus 9 is 12 minus 9. So these two just cancel. So in any one, it's 3 minus 9 is minus 6. So this is the force exerted by this first one, by Q1. What is the first exerted by Q2? So it's K times Q2 times Q3 over R squared. This time it is positive 3, so it's 9 times 10 to the power of 9 times 2 times 10 to the power of negative 9. Negative 9. Sorry, I should just remember the negative there. Negative 9, and that's a negative, and then it's 3 times 10 to the power of positive 9. No, negative 9. Divided by, and this time it's 0,05 squared. Okay, so again, 9 times 3 is 27 times negative 2 is 54 divided by 0.05 squared is equal to 216 times 10 to the power of 1, 2, 3, 4. So this would equal negative 2.16 times 10 to the power of positive 4, but then the same thing happens. The top is a negative 9, so positive 4, negative 9 is negative 5. Okay, so probably what would be better is just to write this one and that one with the same exponent. So let's keep it as negative, this is a bigger number than that one, so it's negative 21,6 times 10 to the power of negative 6. Okay, is that true? Negative 5. If I move it this way, I make it bigger. Yeah, that's true. Okay, so negative 21. Okay, so now we have a diagram here. We have a diagram in this direction, in that direction, and to find the net force, we have to put it head to tail, and then find this. So this would be the net force. Okay, where the one in this direction is negative 88,1 times 10 to the power of negative 6, and this one is negative 21,6 times 10 to the power of negative 6. And it wasn't necessary to do that. You could have just kept it in that form. It wouldn't have made a difference. So don't feel overwhelmed that I did that. So just here we then take, and this is literally just finding the Pythagoras side. So that was 90 degrees there. So this is just a Pythagoras side on here, which is 8,1 times 10 to the power of 6 negative is equal to that squared plus, and then 1,6 times 10 to the power of 6 negative squared. Okay, that looks correct. Is equal to, and then taking the square root of that gives me the hypotenuse, and that is then equal to, so the net force is 2,3 times 10 to the power of negative 5 newtons. Okay, and in which direction? That is, so suppose here when we work this out, let's say, what did they ask? Calculate the net force. So net force will have direction. I just looked if they didn't maybe ask for calculate the magnitude, then direction wasn't important. But we will have to work out direction. So in this case, I would have just said this is west. This is west. This is south. Okay, because it was downwards. And then now to work out the direction of this new direction, let me just go back to my sketch here. To work out the new direction of this sketch down here, I'll need that angle. Okay, so to get that angle is also very easy. All we'll do is take the tan, because we have the we've got that angle in that, or that opposite side and adjacent side, and so let's just see with my calculator now. There we go. So we'll take opposite divided by adjacent. So in this case we can ignore the 10 to the power of negative 6, but again, if you put it in, it wouldn't have a problem. 10,6 divided by 8.1 gives me, and there's the ratio side, and then taking the inverse tan of that, that gives me the angle here, so 69.44. So this is 69,44 degrees, and so this is the answer, 69,44 degrees south of, or let's say southwest. South, so it means south of west. Southwest. Excellent. And that's it. Another question. Next question is asking us, in an unknown point, charge R is placed 3 centimeters away from point P as shown in the sketch below. Calculate the charge on R if the net electric field strength at point X is 0. Okay, so let's just quickly see what's happening here. Shown, okay, so P is that amount, X, okay, is the net electric field at that point. Okay, so when we have 2 electric fields on either side of a when I see the student didn't answer, on either side of a point, that's when we subtract. When they on the same point, so for example, if R and P was on the same point, we would add the electric fields. So beautiful question, I must say, I like it. So let's see, how would we do that? So we would take, first of all, we'll need to start with the correct formula, and in this case our formula is that the net electric field is the sum of the 2 fields. So it's the sum of the electric field at P, sorry, the difference, the electric field at P minus the electric field at R. And so we want the net electric field at that point to be 0. So in other words, that's 0. Now electric field is calculated with this formula. So it's very simple. It's now just substituting in. It's very simple. So you'll see here, electric field is equal to K times Q. So it's K times Q charge of P divided by R squared minus K times the charge of R divided by its distance squared. So if we go back for the values, then you'll see that in the end, all we want is these two to be equal. So in other words, if I all I then want is that KQP divided by R squared. Oh, not R squared. Let's just call these are different R's. They're different values. So let's just call the one RP and the other one RR, just so that we don't get confused. So RP squared, in the end, all we want is that KQ R over R squared R. That's equal. The reason why I did that is because I want to get rid of this K. If I divide both sides with a K, the K is a constant, so it can divide away. I can't do the same with the R's, because this one's R is different than that one's R, because the one is 2 centimeters radius away, the other one is 1 centimeters. But nevertheless, I want to solve QR, so QR is equal to, and now I just multiply both sides with an RR squared, and that then gives me, now I can substitute the points. You could have substituted long ago. I'm just a sucker for formulas, so I'll work with formulas rather than values until I get a final one where I can substitute. So in here I want this distance squared. Again, remember that's in centimeters, so that's 1 centimeter is 0.01 meters squared. That's for R. And then this one is 2 centimeters, so that's the RP. That's 0.02 squared. And then QP, which is now the charge on there, is 8 times 10 to the power of negative 9. And then we just solve it. So 0.01 squared divided by 0.02 squared is equal to 0.05 times, that's literally a quarter, so 0.05 is a quarter, so a quarter of positive 8 is going to be positive 2 times 10 to the power of negative 9. Okay, let me just verify that again. 0.01 squared divided by 0.02 squared. Definitely. Okay, so a quarter of 8. Okay, that's very interesting, I must say. So in other words, if the distance, it's a nice what is it called, a nice multiple choice question, is what must the charge be on this side to be if it's half the distance than that side, in order for it to cancel the other one's charge. But I don't know how to express the question now, but basically what I want to show you is, notice that because this charge is half as, and by the way, this has to be the same sign, because he has to pull him in that direction, and that one has to actually push, because it's a positive charge and we assume X is a positive charge, and so he's pushing in this direction, he's pushing in that direction, and now this one is half the distance closer. So in order to give the same effect as 8 nanocoulombs, that is double the distance away, it only has to be a quarter of the charge. Why a quarter when it's half the distance? Because it's the 1 over r squared. The reason is because we are squaring the distance, and so by halving the distance I can take a quarter of the strength. I don't know if that makes sense, but it's helpful to understand that. Especially in the short questions, this is a very nice short question, high level short question, multiple choice question. Excellent. So next up is our an electricity question. Let's get to that in the next video.